No. Okay. Now you're on my screen. See if other folks joined as well. Very good. Today we have two things in our lecture. One is a lecture part, which is really going into the flexural problems with the lamination parameters and show that some of those problems can be turned into linear programming. In particular, buckling and vibration problems for plates, two-dimensional plates. And the other section is the tutorial that we started last time, implementation of the failure criteria as a linear programming problem. That's the tutorial where we will implement a max strain criterion with the formulation that I started showing last time. That problem is not the easiest one, the one I picked, simply because there are too many constraints. But you will see that it will be fairly easy for you to convert to a simpler form, where you will just use the Style criterion with one constraint per plane. Right now, we have to deal with 5 or 6 constraints. Depending on how you write them. So let me open my lecture charts. These charts are not on the blackboard yet. Flexural. We did this last time. This is the new lecture part of it. And we're just going to look at the formulation. And hopefully as soon as we finish our stiffness optimization problem demonstrating the linear programming approach, we will make demonstration of this particular flexural design, bending design with a tutorial as well. So with that, let me open my charts. This is what I'm supposed to be covering. This we already covered, so we're just going to use the flexural response and the lamination parameters in this lecture. So then put into presentation form. All right. So what we have here is basically we are now getting into the formulation where it's not so simple to decouple these expressions. That there are two in-plane equilibrium equations, one in terms of U displacements in plane along the x direction, and the second one along the v. I think this should have been the v. And then there is the bending part coupled here. This is actually for the coupled cylindrical bending case. I just want to show you so that you'll see that the W expressions are here. If you look at just the bending expression, the simplest form that we can deal with is still nonlinear in terms of these nx, ny, nxy's that multiply the W displacement terms, outer plane displacement terms. However, we linearize this by assuming that anything that happens before bending is in equilibrium, and we find a constant solution or some functional form for nx, ny, and nxy's, and put them as constants in here. So in these expressions, we're going to basically treat them as constants. Now, we'll see later on that there's a simpler problem where we'll just have out-of-plane loads without any in-plane load, in which case all of these terms, we're going to assume them to go to 0, where the bending equation will take the form that bending stiffness matrix D11, D12, D16, D26, and D22 is equal to Q, where we can assume the Q to be some sinusoidal form, in which case its bending expression can have actually closed form solutions from plate equations. So we're going to decouple this, and we're going to basically do only this part without these terms here and with the Q. That's going to come later on. But let's look at the D11 through D66, because in our design, we are literally designing the material properties, the stiffness matrix D, that's what we are designing. And D terms have both the stacking sequence information in it in terms of their orientation and thicknesses buried into these D terms. We've used introduced invariants that we called V0, V1, V2, V3, V4. And in case of balanced symmetric laminates, we'll have only V1s and V3s. These will go to 0. And if you look at the D11 term will have a specific V0D, which is this one here. So let me grab a pen, make that blue, there it is. So we're going to be interested in D11 through D66 terms, and those will be V0D, V1D, V2D, and V3D, and V4D, and they're given as U1 V0D plus U2 V1D, nothing here, U3 V0 V3D. So these were the most generic form. Now the question is, how do we write these V0D, V1, or V2, or V3, or V4D? As I said, we're going to concentrate on balanced symmetric laminates, in which case we're just going to be interested in this column and this column V3D in there. If we go and look at how we define the lamination parameters, we normalized these V quantities, whether it was A or D. In case of A, it was 1 over H, but in case of W1 star now is a normalized lamination parameter. V1 star will be 12 over H cubed times V1D, and V3 star is 12 over H cubed V3D. And if you put the V1D in its place, we come up with a term that will be summation K from 1 to I, where I, these are the distinct ply orientation angles, but this time there is no such a thing as location independent. So in case of in-plane stiffness parameters, we were using I to be distinct orientations. In this case, these are distinct plies, K from 1 to I, and mostly these are going to be 1/2 of the laminate. So this will be N over 2. My N is like that. I can't even write the proper N here. So this is not N, this is N over 2. Let's cross this out. And then these are SK times cosine 2 theta K. Remember, in the in-plane case, we call this V1 star. Now we're calling W1 star. And Sk is not just the difference of the thicknesses. In case of in-plane stiffness, this was portion of the laminate with a specific ply orientation angle, how much of that angle occupies. So the thicknesses between the different plies, Tk minus Tk1, or Zk minus Zk1, were the terms, Zk minus Zk minus 1, which was the thickness. This was the thickness of the Kate layer. This is not true anymore. It really has position information with cubic terms. So these are numbers going from top of the laminate towards the bottom. Each Zk location is a distinct ply interface where I goes from 1 to n over 2, half the laminate thickness. And the Sk is some weird quantity, which is not just simply the thickness. It's the number, but it is not just the difference with the thickness of a given ply orientation angle. And so is the same thing here. And these are cosine 2 theta case, and these are cosine 4 theta case. Now, it turns out that the geometric relationship between W1 and W3 holds, that we have an expression that W3 square, W3 star must be greater than or equal to 2 times W1 square minus 1, where both W1 and W3 stars are in the range from minus 1 to 1. So this is W3 square and W3 star. And this is actually W1 star. So this in-plane diagram for Mickey, Mickey's in-plane stiffness diagram, becomes a bending stiffness diagram. So this is the case, the blue line is the case, sorry about that, where single orientation, when I is equal to 1, there's only one layer, all of those laminates starting with 0 here, and with plus minus 45 are in this diagram along this line, and from plus minus 45 it goes to 90. So this is the case when I equals 1, where W1 star cosine 2 theta and W3 star is cosine 4 theta. And that's this boundary here. Into this, we actually also include the 0, say N1, and then the 90 N2 symmetric, in which case those laminates are going to be the ones along this boundary, horizontal straight boundary, where W3 star is actually minus 1, plus 1. For laminates with I equals 2, then the entire inside of this diagram is the design space. This entire diagram becomes acceptable, and in that case, W1 star will be equal to S1 cosine 2 theta 1 plus S2 cosine 2 4 theta 1. And then a similar expression goes for W3 star, giving you the appropriate equations that will give you any laminate. So two or more orientations, you can basically have any stiffness, bending stiffness term that you want inside this diagram. The question now is, are they linear in terms of the linearization parameters, that is D quantities? If we can express these, show that they are actually linear in terms of this W1 and W3, then some straight lines inside this diagram will correspond to either D terms or some combination of the D terms. Okay? So if you actually go and put these things into the D expressions, you get D11 turns out to be linear in W1 star, provided that thickness is fixed. This is not a thickness design problem, just the orientation angle design problem in that case. And the W3, where use, of course, is material invariance. Those are the constant material properties in there. So is D22, D12, and D66. We are excluding the 26 terms, not because balanced symmetric laminates, those are zero. They are not, as opposed to A26 and A16. D16 and D26 terms are not zero. D16, they are not zero, and D26 is not zero. But they are typically small, corresponding or compared to the D11 through D66 terms, the other D terms that you see here. If the plies are not lumped together, that is, let's assume that you have a 36 ply laminate made of zeros plus minus 45s. And 90s. That's 18 layers half the laminate. So if I look at half the laminate, 18 plus, this is mid-plane. If I lump all the zeros together, all the 90s together, all the 45s and minus 45s together, these terms grow. And the assumption that you make regarding their negligible, they are not anymore. But if you take the zero and then distribute those zeros and 45s, separating them from one another, that is plus, even plus 45 and minus 45, which are the actually terms that will give you the D16 and D26 terms. If you separate these from one another as much as possible, don't put plus minus 45 all together, then these terms negligible compared to the other plies. Nothing, I'm going to digress a little bit and mention a buckling design problem. Can somebody say something, because I'm not quite sure if I'm hearing from my headset. I'm relying on my headset, and I just heard a beep, but it didn't come from my headset. Do I hear you? Do you hear me? Okay, Sam says here. Okay, good. All right, I can. Good. I'm glad that because I thought that somebody pinged me. So let me mention something here. This is the case. Incidentally, these terms. Let me go to presentation mode again. These D16, D26 terms are called bending, twisting, coupling terms. Okay, so when a plate, a flat plate, is bending either along the x direction or y direction, existence of these terms D16 and D26 cause twisting. And what that means is, let's say we take a flat rectangular laminate, completely flat, and put under compressive loads. As soon as this laminate starts experiencing out-of-plane deformation, W super 0, either it goes into buckling mode, it's actually buckling and deforming out of plane. That W is going to be associated with also twisting if these terms are large. If these terms are small, the tendency to twist is not going to be in the laminate. So if this laminate is going to be bending, and D26 and D16 terms are neglected, if you look at the out-of-plane deformation patterns, you will see these nice contour lines, which are rectangular or rectangular-like. So this is the out-of-plane deformation pattern, the contour lines of the out-of-plane deformation, and it's going to buckle like this for small D16 and D26. If, on the other hand, there is large coupling between the bending and the in-plane stiffness terms, as soon as this plate starts going experiencing out-of-plane deformation, jumps again, then you will see, depending on the sign of the buckling, the out-of-plane deformations are going to have a bias towards one direction. So the twisting is going to give you out-of-plane deformations that will be skewed one way or the other. Now, what's the big deal? It turns out that the buckling load of this laminate, this type of laminate where D16 and D26 are large, is actually lower than this one. If you do the computation, this has a buckling load P critical, which is smaller than P critical without D16. So this is with D16, D26, which are large, and this is critical load of a laminate like this, which is without the D16, D26 coupling terms, or they are negligibly small. And this computation is actually tricky, that there are no closed form solutions for this, that you have to actually do this computationally to include the influence of the D16 and D26 terms. So we will not do that. We will always assume that the D16 and D26 are small and our plates are going to buckle in this particular fashion. And if you look at the flexural design problem, basically we can have two of them, which is either under a out of plane load Q. So this is going to be a laminate under out of plane load Q, which we will actually express, and this is typically a function of X and Y coordinate. And this is the, let's say, X coordinate. And let's say X, Y up this way. And we'll be looking at some boundary conditions like this edge and this edge being restrained. So it's going to go into this kind of a deformation shape when it deforms. You can also, and in this case, we will have the D's to be linear in terms of W, that will find a solution for the buckling load deformation W naught, which would be a function of D11 through D66 or D1, 1, 1, 2, 2, 2, and 6, 6. And we'll show that actually that's linear deformation, which means we can design. Or if you look at the vibration frequency, that will be in some normalized fashion in terms of M and N. By the way, there will be M and N in the solution for deformation under transverse load as well. And M and N will come here. These are the mode shapes that will depend on the A over B ratio, the aspect ratio of the plate, where A is the length of the plate in that direction and B is the length of the plate in this direction. So this will be a typical design problem where you say either design the vibration frequencies of the plate and you have to basically compute for the number of M's and N's combinations to see which frequency was the lowest and design for the lowest vibration frequency. But these terms will be linear in terms of W1 star and W3 star, as we showed in the previous chart. So being linear means that it's going to be easy to design. Anything nonlinear, we will not be able to design with the tools that we are looking at so far. We'll actually have to look at a tool that can handle nonlinear optimization problem, nonlinear design problem, and that will be the genetic algorithms that we'll cover in a lecture or two, applied to composite laminate design. So this is pretty much the lecture part. Of course, lectures are typically very easy part of anything that we do. They look rather straightforward and simple, but the devil is usually in the details on how you translate this problem into linear programming problem. And you're going to see that actually will be some interesting variable definitions. In the stiffness design case, we lumped the distinct orientations together, and we introduced ply count variables as integer variables. In this case, we will introduce stacking sequence variables, which actually there will be more than one design variable per ply. being zeros and ones, and we're going to enforce only one of those ply orientations to appear in a given location, not allowing the other orientations to be in the same place, so that we can actually start using these linear design variables in the stacking sequence design, so that you can get a nice stacking sequence distribution through the thickness with all these plies that you may be defining. Even if it's 36 of them, you'll be able to define them very nicely. But there will be increased number of variables. Basically, for each ply, there will be an identity variable for a ply, which they will define it either to be 0, 45, or minus 45, or a 90. So each of these plies can take any of these orientation angles, but a single ply will not be able to take the orientation of all the angles, only one. So it's a 0-1 problem, and if one of them is 1, the others have to be 0. That way, by introducing 4 design variables for this case, for example, we will be able to identify whether it's 0 or 45 or minus 45. Then we have to also maintain the balance conditions with plus minus 45s together. It becomes a little bit more intriguing, but there's a way to do that. So we'll just see how we can do that using the standard tools without going into nonlinear design and problem formulation. So that's pretty much the lecture part. When we introduce the tutorial, we'll also go over some of these equations and make sure that we emphasize them in their right usage in a given application. So that's the flexural design. Any questions so far? In that case, I'm gonna discard these changes and close. Don't save. As I said, I really want to do the linear programming as a sequential linear programming before we go into flexural problems. So I'm going to basically continue the tutorial that we started last time, which is the failure strain integer linear programming as integer linear programming. So let me get rid of all these output cells. All right. Okay, so this was the tutorial that we started last time. Let me open the also version 4. And let me quit local kernel and run all the code for composites. All right, to make sure that it is loaded, I run it and gives me the actual thing. All right, so this was setting up a nonlinear function, which is the failure strains or failure stresses. These are nonlinear functions, but we're gonna linearize them if they are nonlinear. And if the objective function is linear, which if you use the thicknesses, they will be linear. So you won't need to do this linearization for the objective function. We'll just have constraints in each ply, making sure that linear S constraints are going to be satisfied. So linear objective function is just the summation of the thicknesses, and the constraints on the strains. Everything can be expressed from the strains. So those will be P, Q, and R for a stress strain constraint. These are the coefficients of the failure criterion that we are going to use. And we showed how to compute the laminate midplane strain derivatives with respect to the different thickness variable for the thicknesses of zeros and other orientation angles. In this case, we picked up a problem where we said we're going to design only plus 0, plus minus 45 and 90 degree layers. But in order to reduce the number of design variables, I did n layers of zeros and n layers of plus minus 45s, keeping the 90s to be constant, not to introduce another variable in there. And I'm going to execute this entire cell in one go, setting up the design problem. This will be executing all these lines that we covered in the last lecture. Okay, and shift, return. So everything is executed in there. Then we showed the derivative calculations, how it's done. We introduced the load to be a fixed load. As I mentioned last time, you can, if you want, also put parameters in here, alpha and beta, to define different load conditions parametrically. So I'm going to also execute this entire group, showing that I can get actually the strain derivatives with respect to zeros, with respect to 45s, with respect to minus 45s, with respect to 90s. And I'm going to execute all of it. And the advantage that we said by doing it this way, if I want 1.9 as non-integer value for M and N, the specific formulation that we used in defining the laminates will allow us to do that. And that was actually way up there. Let me go back up there again and show. And that was this my A matrix calculation, which set up the A matrix for 0 sub m, plus minus 45 sub n, and 90 degree ply. So this is zeros, plus minus 45 and 90. If you have different orientations, you have to actually rewrite this my matrix, my A matrix module. This is I created as a module in here. This is the only programming that you have to do to be able to do your design. If you have 60s, you put a plus 60 and minus 60 in here, and you can put each layer to be m times the ply thickness, n times the ply thickness. This basically allows to define non-integer thicknesses per orientation angle. So if you have only zeros, 45s, and 90s, their thickness doesn't have to be integer. They can be continuous. And this version of the A matrix computes the properties of the in-plane stiffness matrix for non-integer values of design variables m and n. So this will allow us to do different things with it. So I execute the derivatives. Yes, I executed them, and we showed that actually you get the same results as the other approach. But we also showed that if you go to say 1.9, let's say make it 0.99. So that they're actually very close to these values, 0.44, which is for the integer value of n equals 2. So you can see that they are very close. If you want to make it even closer, you can make a real value 99 and say 99. So these are still real values, but now I'm approaching integer value of 2. And you can see that actually this is 443511. This is 4435. Instead of 11, I have 3. It's only in the 5th digit after the decimal point, the difference. So if you go higher number 999999, this will approach to these values. Now the linearization of the failure constraint. This is the tricky part. If I'm using the max strain criterion, I can say that the epsilon 1 strain in the principal material strain direction along the fiber direction must be less than or equal to epsilon 1 tension allowable. This is allowable in tension, which can be approximated as strength allowable xt divided by E1. The transverse direction, epsilon 2, must be less than or equal to epsilon 2 transverse, that will be YT over E2. And then the compression values may be same as a tension or different. In this case, I'm going to take them to be different. So epsilon 1 compression is XC divided E1. This is the strength along the fiber direction in compression. And this is the strength transverse to the fiber direction in compression. So I have 2 more constraints here. And then absolute value of gamma 1, 2 is less than or equal to shear allowable. If we write it as absolute value in the calculation, it will be 1 constraint. If I impose that as gamma 1, 2 for plus shear must be less than equal to gamma 1, 2 shear, and then the other one is gamma 1, 2 must be less than minus gamma 1, 2 in shear. So that those will be the 6 constraints. Now I'm going to implement the implementation. I'm going to use 6 constraints per ply. So for every ply, K, super K is the ply number. So in the linearization, this super K for each ply, so the G1 super G1 is going to be associated PJ super 1, and that will be ply 1. And then Q1, if it's an interactive failure criteria, there will be one formula that will tie the Q's, P's, and R's together. If not, if it's not an interactive criteria, then P1 super K will be 1 over epsilon 1 in tension, and Q1 will be 0, R1 will be equal to 0. This is the tensile normal stress along the fiber direction. Transverse to the fiber direction is P2, which is going to be 0. But since this is transverse, it will go. This one will go in front of the epsilon 2 relationship Q. So that will be this quantity, and R2 will be equal to 0. And then for compressive, you will have P3 and P4 along the fiber direction, perpendicular to the fiber direction. And for shear, P5 and P6, and R5 will be 1 over gamma 1, 2. R6 will be minus 1 over gamma 1, 2. So that will be the R5, P5, or R5 and R6. P1, P5 and Q5 and P6, Q6 will be equal to 0. So let's say not apply 1, but say apply failure P's, which will be independent of the apply number P1, P2, P3, P4, P5, P6, and P1 will be 1 over epsilon allowable in tension, and P2 equal to 0. P3 is equal to minus 1 over epsilon 1 compression. P4, I stop right there, mass goes to 0. P5 goes to 0, and P6, 4, 5, P6 goes to 0. This should define all of them. So these are the P's, and similar to this, there will be, as you can see, we are doing it as we go along. These are Q's now, and I'm going to replace Q1, Q2, Q3, Q4, Q5, and Q6. This time I'm going to replace these P's with Q's. And you watch out if I make a mistake in typing, warn me. But now the Q's are, this is 0. Q2 will be epsilon 2 tension. Q3 will be 0. Q4 will be epsilon 2 compression with a minus 1. And Q5 and Q6 are 0. And then I'm going to change Q's to R's. And the R's will be 0. This will be 0. R2 will be equal to 0. 3, 0. And 4 will be equal to 0. 5 will be equal to minus shear allowable. Plus shear allowable. Epsilon 1, 2. I will call it A. And R6 will be minus 1 over epsilon 1, 2 allowable. Actually, I called it S, so instead of A, I might as well call this shear. The other one being tension compression, and this is shear. Okay, so these are the Q's and R's given there. Now I'm kind of ready to start writing these expressions. Okay, let's see. K will be the apply number, J will be the orientation, and I will be the orientation as well. Where are my J's? 1, 2, 3, 4, 5. Okay, so J's will be P1 through P5. No, 6, P6. And I can write this expression now. Let me maybe copy this expression so that we can write these things properly. Or at least I won't make a mistake in copying. Let me copy this. Put it here. All right. So I'm going to say G. I'm going to take the first ply to be 0, G1. And the first constraint in there, J1. And I'm going to say linear. Equals, equal. Now I can write that equal line in the I want to define as an expression. I want to define it as an expression. Equals. So the first thing is the constant term, G11. And I'm going to call this T0 for the design point. So I'm going to have to actually compute this value to substitute in here. And then I have summation over I from 1 to 4, 4 different orientation angles. So plus T0 minus I have to find a way to differentiate these from these. These are basically elements of this T0. In the symbol, what do I say? T0. As a constant that will be also known. And then J is 1, so P1, super 1, which will be this P1 here. Now, those P's are not defined. They're still in this form. Do I want to also define all of these? Do I want to replace them? I think I do. So what I'm going to do is this. I'm going to split this line into 2. So what I'm doing is I'm actually assigning the p-values to their corresponding variables p1 through p6, and then the failed p's, that's all of them. I'm going to extend my column in front of this. So I get the same result, but along the way, I also now have P1 equals 1 over epsilon, and P2 is equal to 0. So they do exist in their native form. All right, coming back to here, I have P1. P1, and then the derivative of this term actually be computed in the previous cell. It's just that the symbol for this is not that straightforward. But if you go up here, this is with respect to I equals 1 will be with respect to first design variable is 0, and epsilon 1 is the first element of this P strain with respect to T0. That's this one. And first element is epsilon 1, epsilon 2, gamma 1, 2. All with respect to zeros. Okay? So I'm going to copy this here. As a multiplication. I can put a space or I can put a star. And the first element. So that's this term. Now, I'm going to also write these, but Q and R for this are actually 0. So you will see that I can basically open a parenthesis here, meaning that I'm taking this out. And writing still I equals 1. This is this term here with 3 of them. It's I know it's rather difficult to keep track of what is what, but this is basically epsilon 2 with respect to the 0 degree derivative, and then plus R1 times the third component, which is 0, but that completes this one term in here. Just for sake of showing you, we're not done with this summation, but let's, for the sake of showing you that what that reduces to, we have the Q1. Is that Q1 not defined? Oh yeah, they are not defined. I had to do the same thing for these. And So once these are done, you'll have much easier time. You don't have to do all of these basically. That's what the tutorials are going to do. So this is like extending the office hour to tutorials. So these should do their job. Let's put semicolon here. Semicolon here so that we don't print them again. So we're supposed to be getting the same results as these, but along the way we also define the Q's and R's. So coming back to here, you can see only epsilon 1 tension left with just that term, and this is also 0. All right, so we are doing well, except we need more terms in this because there's summation I from 1 to I in here. So this is with respect to thickness 1, but any change in other plies also change the strain levels in the 0 degree ply that we're looking at right now. So we'll have I is equal to 2 term, I equals to 3, and I equal to 4 term added to this. And those will come as, so this is closing that parenthesis. I'm going to copy this and paste it in here with a plus sign. And now it's the second thickness variable. That's the 0.45. That's going to be a variable. And this is T45. And these will become again B sub J. It's the same J, because J is controlled from here, and it's still 1. 1, 2, 3, it goes like that. P and Q and R. So it's still P1, Q1, R1. But this is not with respect to 0. This time the I is actually 2. That's the derivative of the with respect to 0.45. We called it with respect to F. So this is tedious, as you can see, but better be doing it. With respect to the second design variable, and then plus, now with respect to the minus 45, so I'm going to put here TM minus 45, and this variable for that was of FM. I am basically correcting my own things, and then the 90. One more term. And we'll make that T90. Make this 90. And the variable for it is this guy. Okay, this is one of the constraints. All right. Now executing that, you'll see that once this is given, allowable is given, all of this is going to turn into a constant. And then there will be a linear variable T0, linear variable T45, linear variable T90, linear variable minus 45. And their base value is T0, T45, T90, T minus 45. We're going to put those later on. And there will be also a constant for the base stress evaluation. So this is one of the constraints. G11. Now, we go to copy this and paste it. Now we're going to do G12, which will require P2, Q2, R2. Okay. So we're changing J to 2, still in the first layer. And this will become G1 to 2. Same variable, T0, T, and the only changes, these will become P2, Q2, R2, P2, Q2, Q2, R2. This is the second constraint. For the first layer stuff, I'm going to put a, let's say, around this 2 to make sure that everything is in the right order. Very good. Except there's epsilon 2, epsilon 1 here, epsilon 1, epsilon 2, for 45. The third constraint, same thing. With the PQR with the 3s. I'm going to put a semicolon in there. And the fourth, G14. And I'm going to change the PQRs later on. I could have done this as matrix form, but I don't know how easy it will be to follow in the matrix form. So I'm going to look at it to see if I can actually simplify it, but I will leave these as they are because there are now 6 constraints for the first ply, which is a 0 ply. And these we're going to change to 3s and 4s and 5s and 6s. And then all of that is going to be repeated again for the second ply, which will be G2, 1 through G1, G2, 6. And then the minus 45 degree layer and the 90 degree layer. 4 different distinct orientations. So there will be a total of, what is 4 times 6? 24. 24 constraints. But they're going to be linear. And we're going to solve those in the next lecture. I'm just going to show you the solution in the next lecture without going through this formulation. I'm going to assume that now you're going to be actually knowing all of these formulations. Let me copy it and paste it here for the second layer. And merge these cells together. That wasn't the way. This was the way. And this will be 2, 1, 2, 2, 2, 3, or 2, 3, 2, 4, 2, 5, and 2, 6. This is for the plus 45. And again, I'm going to change some of these things in here to make sure that we get the right values. So that's it for this, and this will be finished form next time, and you're going to get it. And next time I'll also define the test 2 so that you'll be ready to go and take whatever I have and turn it into a problem where you're going to be applying this to the design problem that you did the first test. Okay? With that, I conclude. Any questions? If you're asking when the test is going to be due, second test, I think I'm going to assign it to Thursday, and I'll give you guys 2 weeks to finish that. That would probably have been one of the questions. Any other questions? And I'm going to put these on Blackboard on Thursday as well. Questions? Oh, I forgot to turn my camera on. Now you see me. If no questions, I'm gonna stop recording. All right. And you get my emails and you ask questions. Samuel, I did, but I keep forgetting to look into it. I'm so sorry. This